In web development these days, we often hear the term web API or web services or REST API or RESTful web services and lots of permutations of these terms. In this video, we'll talk about where all these terms came from and in particular, the history and evolution of web services, the two types of web services used today, and their pros and cons. It all started with network programming, especially in a client-server architecture. Usually, a client will need to send some data to a server, the server processes it, and sends back some result. For example, suppose we want to send username and password to a server, and the server will check some database. If the username and password are valid, the server sends back the user information like first name, last name, and age. And if the username and password are not valid, the server sends back user not found. This seems to be a pretty simple problem, but if you have to implement it, you realize that it takes lots of code to do this simple thing. Note that I'm talking about real low-level networking code, not some web application code where the networking part is actually already taken care of by some libraries and a web server. If you took a networking class before, you probably wrote this type of code before called socket programming. On the client side, you have to create a socket, and in order to send username and password, you have to write two strings to the socket, and then to get the results back, you have to read a string from the socket, and if that string matches user not found, you'll return a null value as the user object. Otherwise, you read another string and another integer from the socket, and then construct a new user object, and then you have to close the socket. So this is just for the client-side code. The server-side code is even more complex, which I'm not showing here. On the server, not only you need to deal with socket like on the client side, you also need to handle multi-threading or multi-processing. You'll need to use a main method or process to listen to a socket, and when a client connects, you need to spawn a new thread or process to handle that client. As you can see, it's really lots of code for a fairly simple problem. And it's not just lots of tedious code. Another less obvious but still very important problem is that you have to design a different data exchange protocol for each different application. For example, in our case, if the server responds with user not found, we return a null user object. This convention or protocol, if we can call it, is only useful for this particular application. For another application, you'll need to come up with a different convention. Not only this is tedious, it's also error-prone. For example, if a user has a first name called user not found, your code will break. So some very smart people came up with a great idea. The first observation is that many of these types of client-server interactions can be modeled as function calls. The client calls a function and gets some results. Of course, unlike a regular function call, the arguments of the function must be sent to a server, and the return value must be sent back. And here comes the second important observation. We can build a library to send the arguments to a server and send the return value back. And this library doesn't need to know anything about the application, because all it does is send some data over and then get some data back. It doesn't really need to know whether the data is a username or password or something else. And this allows us to build a library that can be used by all applications. And this is the idea behind RPC, or Remote Procedure Call. RPC was implemented in C. You can't use it easily with a language other than C or C++. So later, Java implemented its own RPC called RMI, remote method invocation. By the way, if a function can exist by itself, we call it a function. If a function is part of a class, we call it a method. There's actually no function in Java, only methods. So the Java RPC is called remote method invocation. The first thing about RMI is the interface. We have to create an interface that defines the methods to be invoked. This interface is needed by both the server and the client. The server needs to know what methods to implement, and the client needs to know how to call those methods. On the server side, of course, there's an implementation of the service interface. This implementation is often called a remote object, in the sense that the client will call the methods of this object remotely, of course. The server also has an RMI service registry. A remote object must register with this registry, and the clients can look up this registry to find the remote object they want to invoke. Then, of course, the client side. A client would first connect to the registry, look up a remote object, and then call a method. Here's an RMI example. First, we have the interface called auth interface. There's one method in the interface, authenticate, which takes a username and a password and returns a user object. RMI requires that a service interface must inherit from the remote interface, and the remote method must throw the remote exception. For our purpose, these requirements are not really important. And this is what the user class looks like. Just a regular Java class with some getters and setters. The only thing that's a little special here is that the user class should implement the serializable interface. The serializable interface, if you recall, is a way to tell Java virtual machine that objects of this class can be converted into binary form and back. And this is necessary because we are going to send user objects from the server to a client over the network. On the server, we have an implementation of the auth service. The actual implementation, again, is not really important. Just know that we have two users, John and Jane, with password ABCD and 1234. RMI requires that a service implementation must inherit from a remote object superclass. Again, for our purpose, that's not really important. To make this service available, we can create a registry. A registry is a server by itself, and ours will be listening at the port 4048. And then we register the service implementation with the registry under the name of service. Then on the client side, we can connect to the registry by providing the host name and the port number. And then we look up the remote object by name, and then we call the remote method. Most of the code is straightforward and makes intuitive sense. Let's run it, and then we'll talk a little bit more. So first, we need to start the server side by starting the registry plus registering a auth service implementation with it. So let's run this one. And then we can run the client. And the client gets John and age 20. So we also, if we, let's say, if we give the wrong password, and if we run this again, it will get a user not found. If we go back to the server and stop it and try to run the client again, we'll get an exception that says connection refused to host, and this tells us that the client indeed is trying to invoke a remote method, not some local method. As I said, the code is pretty straightforward, and since we're not really learning RMI per se, we don't really need to worry about the details about remote object, remote interface, and all that. One thing, however, that's somewhat not intuitive or a common mistake when people try to understand is that what is this registry lookup? What does registry lookup return? A common misunderstanding is that when we call registry lookup and give it a name, this call will return a copy of the remote object, and then the remote object will be invoked on the client machine, and that is not correct. Remote objects never leave the server because they may not even function outside the server. For example, if they rely on some resources on the server. The object returned by registry lookup is commonly referred to as a stub or proxy. It's not the real remote object, just something that implements the same service interface. When a method in the stub is called, the arguments of the method will be sent to the server, and the actual remote object will process it and send back the result. And then the stub will return the result as a return value. This diagram shows the whole process of RMI. Notice that on the left-hand side is a client, and the right-hand side is a server. The remote object never leaves the server, and the method directly called by the client, this method, is actually a method in the stub or in the proxy object. So once we can make remote function calls using one language, whether it's using C or C++ or Java, the next natural step is to do it cross-platform. If you think about it, there's no reason why the server and the client must use the same language. After all, they just pass data between each other. It should be possible, for example, to implement the server side using Java and then call the functions on the client side using another language like C or Python or PHP. The idea is natural and straightforward, but there is a pretty big obstacle, and that's how we define the service interface for multiple languages. When we use the same language on both the client and the server, it's simple. For example, if we use Java, we can define the service interface using a Java interface, like what we're doing here. However, if the client side uses something else. For example, if the client side uses Python, then of course Python cannot use an interface, Java interface. And then what can we do? How can we make this RPC idea work for multiple languages? One cross-platform RPC technology which was very popular for a while is called CORBA, Common Object Request Broker Architecture. CORBA solved the interface definition problem by introducing a new language called Interface Definition Language, or IDL. IDL is not a real programming language. The sole purpose of IDL is to define service interfaces, or in other words, APIs. This is what an interface defined in IDL looks like. I actually wrote something like this when I was taking a class in graduate school, which was many years ago. In this example, we have an API for managing bank accounts. As you can see, it defines a method to query the balance given an account number, a method to set the balance, a method to set the address, and so on. So once you establish this new language IDL, people can start writing translators to translate an interface written in IDL like this into languages like Java, C++, Python, and so on. So now the client and the server can use any language they want. CORBA was popular for a while and was backed by many of the big companies in the industry. But because of some technical and political reasons, it eventually faded out. At the end of the slides, I linked to an article called The Rise and Fall of CORBA. You can check it out if you are interested in some computing history. After CORBA came web services, or what I call traditional web services, to distinguish them from the RESTful web services that we'll talk about later. If we have to summarize traditional web services in one sentence, we can call them RPC over HTTP. It's basically RPC, but instead of using low-level networking communication protocols like TCP or UDP, it uses HTTP. This is where the name web services came from, as it uses the same protocol the web uses. Over the years, people actually developed many web service protocols. Some were intended for a particular programming language, some were language independent, some encoded their messages in binary form, and some used text. Most of these web services were not widely used, except for one called SOAP, with an interface definition language called WSDL. We'll see an example of how traditional web services work, and in the example, we'll use the web service library provided by the Metro project. Traditional web services are very difficult to implement without a good library because the specifications are so complex. Years ago, when I first programmed web services, it took lots of code just to do very simple things. Over the years, the libraries have improved a lot and made implementing web services a lot easier. The library we'll use is from the Metro project. It was originally developed by Sun, and then Sun was acquired by Oracle, and then Oracle transferred the project to the Eclipse Foundation. This library implements the latest Java web service specifications, guarantees interoperability with Windows Communication Foundation, and above all, for our purposes, at least, is quite easy to use. And this is the sample project. Let me close the ones about RMI and look at the ones for web services. So, by the way, if you want to run this sample project, you'll need to use JDK 8 instead of 11. All the Java EE tools and packages are moved out of JDK after 8. So it will take quite a bit more work to run it with JDK 11. And I'm not going to do that for a sample project. In case you don't know, it's also quite easy to have both JDK 8 and 11 on the same computer and switch back and forth. For example, you can just download JDK 8 and 11 in zip files and then unzip them into different folders. And if you want to use one of them, and all you need to do is to specify the one that you want in the path environment variable. So here I set the path to the JDK 8, so I'll be using JDK 8. And in Eclipse, you can actually include both at the same time. So if you go to Java and then installed JREs, you can see that I have included both at the same time. And right now, 8 is the default one, but if I want to use 11, I just check 11. So this way you can easily switch back and forth between 8 and 11. It's not really a big issue. Okay, so back to the project. We'll need a web service dependency, and that dependency is called web service-rt. And then, of course, we need to implement the web service. And here is the implementation. So here, as you can see, we can implement web services using regular Java classes and methods. So this is just a regular Java class, and inside this class, I have two methods. One is called MD5 and one is called SHA1. The MD5 one will return a MD5 hash of a given string, and the other one will return a SHA1 hash. Again, the details are not important. Just think of them as two methods that we'll call remotely. If we want to make these two methods available as web services, all we need to do is add some annotations. So just annotate the class using annotation web service, and annotate the methods you want to expose as remote methods as with web method, and that's pretty much it. So this handles the implementation part. And then we need to make the methods available online, and that means we need to run some type of web application. The good news is that we don't need to write any code, just some configurations. So here, first we have the web.xml file, which is usually needed for a Java web application. And notice that the only thing here is a listener class from that library. And this class, listener class, will load another configuration file with some information about the web service. And in this file, we give the web service a name called hash service. And we specify which class implement the service, and we specify a URL where the service can be accessed. And that's it. Now we can run this application and make the web service available. So let's run it, and this time we need to run it on server. Okay, so now the web service is running and it seems like nothing is happening. I have a index.html file here, and you can see this is the source code. There's really nothing in here other than a link. So if I click on the link, we can see that there's some information about this web service, the service name, something called port name, and something else. But it's not entirely clear how we can use this web service. Well, the key about using a web service is the WSDL part. WSDL, as you can probably guess, stands for Web Service Description Language. It's a language for describing web services, including where the service is, what the service does, how to invoke the operations of the service, and so on. The role of WSDL is basically the same as IDL in CORBA. You have a language that describes APIs, and a description in this language can then be translated into other programming languages that want to call this API. So let's see what a WSDL document looks like. Let me show it in the bigger browser. So, well, it's in XML, so it's quite verbose. But if you read it carefully, you can kind of tell what's going on. For example, you can see something called port type, which seems to be the name of the web service. And then you can see something called operation, which seem to be the methods. And then you can see something called input and output, which seem to be the parameters and return value, and so on and so forth. We won't get into the details of WSDL syntax, but I do want you to be able to read a WSDL document and understand what's going on. The key for that is to understand how we can describe an API. So take this one as an example. How do we describe this interface? Well, we need to specify the name of the interface, the name of the method, and then we need to specify the types of the parameters and the type of the return value. And that's about it. Note that we don't need to specify the name of the parameters. For example, it really doesn't matter whether the parameter, the first parameter is called A or B or whatever. Any code that calls this method simply needs to know that they need to provide a string value for the first parameter, and that's enough. So in other words, the order of the parameters already give enough information, so we don't need to give parameters individual names. Knowing that, if you read the WSDL document again, you can see that port type is indeed the interface name, operation is indeed the method name, input indeed the parameters, and output is indeed the return value. Here, the message attribute specifies a type, and here it says TNS column MD5. Using our knowledge about XML namespace, we can see that the TNS namespace is here, and the schema location for that TNS namespace is here. So we can actually go to that URL and see the XML schema document for the types. So here it's clear that the type MD5 is a complex type in XML, and it contains a sequence, and this sequence only has one element, and that element is a type of string. So by looking at this document, you can see exactly how the types are constructed for the web service methods. So now we know what WSDL is. Let's see how we can use it to call a web service. We'll use the WS import tool in JDK to generate the client-side stub code from WSDL. And again, this thing requires JDK 8 or 1.8 if you want to call it. So first, let's go to the project folder, which is WS, and then we'll run this command. Actually, I think I can, yeah, I can get the command from here. So we'll run this command called WS import, and D is the folder where the generated code will go. P is a package for the generated code. This one will say keep generated source code and do not compile it. And the location of the WSDL document is, of course, this URL. So if we run this, it will generate a bunch of code, and if I refresh here, you can see all the generated code. So from the WSDL document, it will create an interface, and it will create a bunch of types and all the other necessary code. And then in order to invoke that web service, all we need to do is to create a hash service, which is generated from the WSDL document, and then call get hash service port, and this will give us a stub for the remote hash service, and then we can then call MD5 and SHA1, and let's run this. It will output the MD5 hash of ABCD and then SHA1 hash of ABCD. So to see that these two method calls are indeed invoking web service methods, we can go to the server and then stop it. And then we can try to run this again. It's running. Okay, so this time it gives a error and say fail to access WSDL at this URL and connection refused. That's because we have stopped the server, and that also shows that this one is indeed calling a web service method, not some local method. Okay, so this is how we can use a traditional web service. And as for traditional web services, WSDL is the language to describe the API, but we do need another protocol to define the format of the data exchanged between the client and the server. And that protocol is SOAP, or Simple Object Access Protocol. SOAP will package data in SOAP messages, and these messages are sent over HTTP between client and server. This is an actual SOAP message from many years ago when I taught this class. At that time, Google provided a web service that allowed people to get spelling suggestions. For example, you could send Britney Spears to the service. Note that the double E in the last name. And the Google Web Service would send back the suggested correct spelling, the EA in the last name. And if there's an exception, there would be a SOAP fault response message that looked like this. Data types are an important thing in web services. In SOAP, data types are specified using SOAP encoding. SOAP uses data types specified in XML schema, like integers, floating point numbers, and strings. And it also supports composite data types, collection data types, and various rules about things like default values and serialization. So at this point, you may be thinking that although SOAP stands for Simple Object Access Protocol, it seems like it's anything but simple. And you'll be correct. As we'll discuss later, the complexity of SOAP is in fact part of the reason for its downfall. There's one more protocol I want to mention to round out what I call the traditional web service stack, UDDI. Remember in RMI we have a service registry where clients can look up services. UDDI is a protocol for registries for web services. It defines a web API for publishing, retrieving, and managing information in a web service registry. UDDI envisioned two types of registries, public registry and private registries that company can maintain internally. Registries can be affiliated with each other and publish services with each other. There are subscriptions and replications and all the other stuff. It was a good vision, but the vision was never realized, at least the public registry part. Many years ago, IBM maintained a public UDDI registry, and I think Microsoft had one too. The problem was that you couldn't really find anything useful in there. Almost all the services in those public registries were things like homework by students who are taking a web service class. Right now, there might be private registries in some big companies that I don't know of, but public UDDI registries are no more. In general, in recent years, the popularity of traditional web services have declined to almost nothing. There are two reasons for that. First, the protocols are just too complex. They are based on some very complex specifications, and it's very difficult to create supporting libraries. If you use a language backed by a major company like Java or C#, you are okay because those companies pay lots of money and have lots of engineers to develop those supporting libraries. But if you use a language that doesn't have major commercial backing, like PHP or Ruby or something, you are out of luck because without supporting libraries, it's virtually impossible to develop web services. And what do you get for all that trouble? Well, it's not even very efficient. For example, here, notice that the only useful thing in this SOAP message is the string Britney Spears. But SOAP requires that we send all the other stuff, which is a waste of bandwidth. And our code has to parse all the other stuff in order to get this one string, which is a waste of time. So this leads to the so-called RESTful web services. This is what a RESTful web service may look like. It will give you a URL pattern like service, user, and then followed by a ID value. And if you want to get a user object, you can just send the HTTP request to that URL with an ID value, like 1, and you get a response back. The response is usually in either JSON format or XML format that look like this. Immediately, we may have some questions like, why are we calling this web service? We know web service is about making remote method calls. So where is the method here? And why does it look more like a web application? And the last but not least, why is it called RESTful? Well, first of all, if you think about it, it does look kind of like a method call. The URL pattern is kind of the method name, and the values in the URL are kind of the method parameters. And the response is, of course, the return value. However, note that there is a very important difference here. In traditional web services, the client code gets an object back directly, like here. But in this case, we'll have to parse the response ourselves in order to get the returned object. This is the reason why the response is almost always in JSON or XML format, because they are natural formats for representing objects, and the parsers for those two formats are widely available for most languages. And what about this thing looks more like a web application than web service? Well, this is actually a good thing. Now, all web languages and technologies can be used to create web services, not just the ones that can afford to pay people to implement complex specifications like so. So now PHP and Ruby people are happy. But why is it called RESTful? Well, the name REST was introduced by Roy Fielding, who is an influential figure in the web community. He was involved in the creation of many specifications related to the web. In his PhD dissertation, he studied network-based software architectures, and the REST is a term he used to describe the common characteristics of scalable, maintainable, and efficient distributed software systems. According to Roy Fielding, these systems share 5 common characteristics, plus an optional one, and these are known as the REST constraints. First, the system should have a client and server architecture, and then it should not maintain internal states, because maintaining states is expensive and prevents scaling. It should support caching, of course, and the resources in the system should be uniformly accessible, like having URLs and URIs. And the system should have a layered or tiered structure. And optionally, it should support code on demand. Think of code on demand like something like JavaScript. You go to a web page, it automatically downloads some code, which will then run inside your browser. So why are these new web services call themselves RESTful web services? Well, they want a catchy name, of course, but besides that, from a technical perspective, they want to mimic the largest REST system, the web. They use URLs to represent resources, like objects. They use request methods to represent operations, and most importantly, they do not keep session data, so they are stateless. That meets an important REST requirement. So if we say traditional web services are RPC over HTTP, the RESTful web services are basically web applications for programs. The users of regular web applications are human beings. though the responses of regular web applications are web pages that humans can read. The users of RESTful web services, on the other hand, are programs that try to access an API, and that's why RESTful web services produce JSON or XML responses. Over the years, RESTful web services also gained many other names like REST Web Services or REST Web API or REST API or just Web API. They all mean basically the same thing. Recently, I tend to prefer the term Web API. It's a fairly accurate term and it's also general enough to include things that doesn't exactly follow REST. So I'll try to just use Web API later on. Here's a quick summary of the alphabet soup we covered in this video: RPC and RMI, CORBA and IDL, the traditional web service stack, SOAP, WSDL and UDDI, and the new RESTful web services. And here's the article talking about the history of CORBA and the beginning of the traditional web services. It's an interesting read. Plus, there are lessons we can learn from the success and failure of the technologies in the past. So, this is the end of this video. See you in the next one.